Once we have seen how it is possible to use switching algebra to formally represent both the specification and implementation of a combinational circuit, we can begin to study the related synthesis process. Combinational logic synthesis consists of identifying a possible implementation, represented by a Boolean expression, for a given specification described by a truth table. Combinational synthesis can be divided into two sequential steps: the translation of the specification into an initial solution, which is easy to compute, and the optimization of the initial expression with the goal of identifying a final expression that is optimal according to a criterion called the figure of merit. A possible initial solution to the combinational synthesis problem can be represented by the first canonical form. We adopt this solution because it is unique and easily computable. To give you an example, this slide shows the truth table of a function to be synthesized along with the corresponding expression in the first canonical form. When the specification contains don't care conditions, these can be considered as either 1 or 0 in generating the solution. For example, consider the following specification where the value 7 represents a don't care condition. We can derive two different expressions in the first canonical form. The first treats 7 as part of the offset, thus excluding the corresponding product term from the expression. The second treats 7 as part of the onset, thus including the product term x, y, z in the expression. As we will see, don't cares can be opportunistically exploited by assigning them the value 0 or 1 to optimize the resulting circuit. It is also necessary to define the reference model to be adopted for computing the optimized expression. The reference model allows us to narrow down the set of possible alternative solutions to analyze during logic synthesis, which would otherwise be too vast. Since the first canonical form, representing the initial solution, is defined as a sum of minterms, or more generally, as a sum of logical products, it is convenient to use an expression composed of a sum of logical products, abbreviated as SOP, as the reference model for the optimized solution. For this reason, we will talk here about two-level combinational logic synthesis, since the resulting circuits, represented by sums of products, will consist of a first level of AND gates and a second level of OR gates. A final note. In this course, we will address the synthesis problem by focusing on expressions in the sum of products form. However, it is also possible to approach the problem from the dual perspective, applying the same methods we will study to expressions based on the second canonical form and the product of sums. A first approach to performing combinational optimization consists in iteratively transforming the first canonical form and the derived expressions by directly applying the properties of switching algebra. Let's clarify the idea with an example. We want to optimize the following expression in the first canonical form, considering as the figure of merit the number of literals present in the expression. For now, we introduce the use of this figure of merit, which will be discussed in detail in the next lesson. First, we calculate the cost of the initial expression. The number of literals is 9. We can then proceed by sequentially applying a series of axioms and properties of the switching algebra. Specifically, we apply the distributive property. Then, we remind that x or not x is equal to 1. We consider that 1 is the neutral element for the logical product. Again, we apply the distributive property, the simplification property, and finally, the distributive property again. We then stop, obtaining a minimal sum of products expression, whose cost is 4 literals. This example raises two questions. How did we select the sequence of axioms and properties to apply? How did we determine that the final expression is optimal? The answer to both questions is by eye, or more precisely, by intuition. Something a human has, but a computer does not. Let's redo the exercise. This time we apply the idempotence property, the distributive property. Then we remind that x or not x is equal to 1, and we consider that 1 is the neutral element for the logical product. As we can see, we arrived at the same solution through a different procedure, applying a different sequence of transformations, once again selected by intuition. In conclusion, the direct application of algebraic properties does not allow us to identify a systematic procedure. Therefore, it is not possible to define an algorithm that systematically transforms the logical expression and determines whether an obtained expression is optimal. Hence, it is necessary to tackle the problem of combinational logic synthesis with other approaches. Approaches to combinational synthesis have been extensively studied in the past. We can divide them into two groups: exact methods and heuristic methods. The exact methods identify the best possible solution by theoretically comparing all possible alternatives. Their limitation lies in their computational complexity, which grows with the size of the problem, leading to execution times that become too long and therefore prohibitive. In contrast, heuristic methods find a solution that is not optimal but good enough, in a reduced computation time, by wisely deciding which alternatives to evaluate. Since this is an introductory course on digital logic design, we will study two well-established exact methods for two-level combinational logic synthesis: the Carnot's method and the Quine-McCluskey method.